Welcome back. Having explored drug metabolism, we now turn to the final step of pharmacokinetics, excretion and elimination kinetics. Excretion is how the body removes drugs and their metabolites. The kidneys handle most of this work, but the liver, lungs, intestines, skin, milk, sweat, and saliva also contribute. Understanding these pathways and their kinetics is essential for safe and effective drug dosing. Renal excretion is the primary route. Three processes determine how much drug ends up in the urine: glomerular filtration, tubular secretion, and tubular reabsorption. The functional unit is the nephron, where blood is filtered at the glomerulus, drugs are actively secreted into the tubule, and water and selected molecules are reabsorbed back into circulation. Glomerular filtration is a passive process governed by four key factors. First, molecular size. Smaller molecules pass easily. Large ones like insulin, heparin, and dextran cannot. Second, plasma protein binding. Only the free, unbound drug is filtered. Warfarin, for instance, is 98% protein bound, so only 2% gets filtered. Third, renal blood flow. Higher perfusion means greater filtration. Fourth, ionization. Ionized drugs are filtered but not reabsorbed, leading to rapid excretion. Tubular secretion is an active, energy-dependent process in the proximal tubule. Transporters like organic anion transporter, organic cation transporter, P-glycoprotein, and MRP2 pump drugs from blood into the tubule. Unlike filtration, protein binding doesn't limit secretion. As free drug leaves, more dissociates from proteins. A classic interaction: probenecid blocks penicillin secretion, prolonging its half-life. Salicylates similarly reduce methotrexate clearance. Tubular reabsorption is passive and depends on urine pH and lipid solubility. The principle is ion trapping. Ionized drugs stay in urine and are excreted, while unionized lipid-soluble drugs diffuse back into blood. This means urinary pH can be manipulated. Alkalinizing urine accelerates the elimination of weak acids like barbiturates and salicylates. Acidifying urine speeds removal of weak bases like morphine and amphetamine. Strongly ionized drugs are excreted readily at any pH. Beyond the kidneys, drugs leave the body through several other routes. Biliary excretion sends drugs like ampicillin, erythromycin, and corticosteroids into bile, eliminated via feces. Fecal elimination handles unabsorbed drugs and those secreted by P-glycoprotein in enterocytes. Alveolar excretion clears volatile anesthetics, nitrous oxide, and alcohol through the lungs. Drugs also pass into breast milk. Basic drugs concentrate there due to acidic milk pH, and into sweat, saliva, and skin in smaller amounts. Now to elimination kinetics. Most drugs follow first-order kinetics, also called exponential kinetics. The rate of elimination is proportional to plasma drug concentration, meaning a constant fraction is eliminated per unit time. The equation is C equals C naught e to the minus KT. Plotting concentration against time gives an exponential decay curve, but when we plot log concentration against time, we get a straight line. The slope reveals the elimination rate constant K. Half-life, written T-half, is the time taken for plasma drug concentration to fall to half its value. It equals 0.693 divided by K, or 0.693 times volume of distribution divided by clearance. Half-life is independent of dose and route. After one half-life, 50% of the drug is gone. After 2, 75%. After 3, 87.5%. After 4, nearly 94%. And after 5 half-lives, about 97% is eliminated. The same rule applies to reaching steady state during continuous infusion. It takes 3 to 5 half-lives. Some drugs follow zero-order kinetics, where a constant amount, not fraction, is eliminated per unit time, regardless of concentration. The plasma concentration drops linearly, while the log plot becomes curvilinear. This happens when the eliminating enzymes are saturated. Classic examples include alcohol, phenytoin, warfarin, and theophylline. A related pattern is mixed order, or Michaelis-Menten kinetics, where low doses behave first order, but high doses become zero order. Aspirin, digoxin, and phenytoin show this. small dose increases can cause dangerous toxicity. From the filtering glomerulus to the exhaling lung, from exponential decay to enzyme saturation, drug excretion and elimination kinetics shape every dosing decision in medicine. Master half-life, clearance, and order of kinetics, and you can predict how any drug will behave in the body. This completes our journey through pharmacokinetics. Thank you for watching.